All right, the last add-on I'm going to throw in here, and this is working with substitution, the method of substitution, with definite integrals. How do you work the substitution method with definite integrals? Remember, with definite integrals, our answer needs to be a number. It turns out there are two methods. Students always want to know which method is shorter, which method is faster, which method is easier. Neither one. They are both have exactly the same steps. It actually is precisely the same computation. It's just at a different place in the procedure. You should be familiar with both of these so that when you go to university of wherever you're going, Professor so-and-so does method number 2, you should be familiar with what that is. Even though most students gravitate, and most instructors gravitate to method number 1, you should be familiar with both of these. They each have advantages and disadvantages. And so here we go. The procedure starts the same. The key is everything here is in the X language. Remember what we have here. Just conceptually, we have a graph of a function. This is not the graph of that function, but we have the graph of this function, and we're going from 1 to 2. And conceptually what we're saying is we have some region. One of the interpretations of this process is we're finding the area of that region from 1 to 2. But here's the point. This is the x-axis. Strictly speaking, this is x equals 1 and x equals 2. And so just for a point of emphasis, I'm going to write this is, instead of writing integral from 1 to 2, I'm going to write this. You don't need to, but I'm going to just for emphasis, this is x equals 1 to x equals 2. And this is x equals 1 to x equals 2. Just to emphasize, the limits of integration are also in the X language. Now, we start the same as before. Let u equal the stuff in parenthesis, larger exponent, stuff being raised to a power, all the same indicators as before, x to the second plus 1. We need to create 4x dx to get the substitution exact. Well, what do we have? The derivative here is 2x dx. Don't want 2x dx, I want 4x dx. Multiply both sides of this equation by 2. And the substitution is exact. So, here is the issue. 4x dx is now 2 du. X squared plus 1 to the second power is now u to the second power. But what I'm going to write now, what I'm going to put up here now is wrong. Watch, here comes wrong. If you put 1 to 2 here, that is wrong, and do you see why it's wrong? Everything here needs to be in the U language, but these limits of integration are in the X language. You're mixing the languages if you go from 1 to 2. So rather than do this, what needs to happen is this. This is option number 1. Option number 1 is you translate the limits of integration as you go. So below this let statement area, here are my limits. Upper. And use the let statement. U is equal to, use the let statement evaluated at the upper limit. That's 2 squared plus 1 is 5. The new upper limit of integration is 5. The lower limit of integration, u is equal to, plug 1 into the let statement. This is 1 squared plus 1 is equal to 2. So the new lower limit of integration is 2. X equals 1 to x equals 2 is the same thing as u equals 2 to u equals 5. It's not obvious this procedure does what we say it does, but the geometry, it turns out, does bear this out. So this is method number 1, and this is usually the most common. You translate the limits as you go, and now just complete this out. This is now this is now 2 times u to the third over 3, yeah? This is now evaluated from 2 to 5. This is now This is now 2 times 5 to the third over 3 minus 2 times 2 to the third over 3, which is 125 times 2 is 250 thirds minus, this is 16 thirds. And 250 minus 16, if my arithmetic is correct, is 234 thirds. If my arithmetic is correct, that's 250 minus 16 is 234 thirds. That's correct. Method number 2 is this. Same. In fact, I'm not even going to write it. It's the same. You would let, here, let's do this here. I'm going to run out of space if I'm not careful. Let u equal x to the second plus 1. du is 2x dx. I don't want 2x, I want 4. So 2 du is equal to 4x dx, and the substitution is exact. So, this method does this way. I have my 2 multiplier integral. I have u to the second du. But rather than translate the limits of integration, you put in a and b. These are dummy limits. They're numbers that we're not going to worry about what they are yet. Just put in some numbers. X equal 1 translates to something, we don't know what it is. X equal 2 translates to something else, we don't know what it is. Now, do the antiderivative. This is now 2 times u to the third over 3. This is now evaluated from a to b. We don't know what a and b are. But now, go back to the original x language. This is now 2 times, what was u? U was x squared plus 1 to the third over 3. But since we're in the original x language, we don't need these placeholders. We can now use the original limits, 1 to 2. And then you substitute upper limit into here. That's exactly what you would get here, right? Substitute lower limit into here. That's exactly what you would get to here. So from here, it merges precise. Well, here, let's do this. I'm going to run out of space. Let me continue this problem up here. So I take 2 times, this is now 2 to the second plus 1 to the third power over 3 minus, evaluate the lower limit, 2 times 1 to the second plus 1 to the third over 3. And notice what happens. This is 2 to the second plus 1 is 5. 5 to the third power is 125. 2 times 125 is 250. Where did that come from? This is 2 to the second plus 1 is 5. This is 1 to the second plus 1 is 2. And notice, we are at precisely this location. It is precisely the same computation from here on out. Students want to know which one is the same. It's the same computation. Here you do 2 to the second plus 1 up in this location. In this method, you do it down here in this location. You do 1 to the second plus 1 in this location. In method number 1, you do it in this location. So it's the same amount of work. Usually students gravitate to this level, to this procedure, but either one is allowed. You may translate the limits as you go and then evaluate and be done, or put in placeholders, go back to the original variable and evaluate and be done with it. You get the same result either way, 234 over 3.